Hello students, welcome to the class of Control System 2 followed by the code EE603. Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. We will discuss on the solution of state equation and the state transition matrix. In this video, we will discuss on solution of state equation, the state transition matrix, its properties, the solution of non-homogeneous equation, methods which are used to find the state transition matrix, the problems with and references and MCQ. First is a solution of state equation. Now we are familiar with linear control system, and when the linear control system is subjected to both inputs and the initial conditions, then we get the total response, and the total response is equal to the zero state response plus the zero input response. So what is the zero state response? Now the zero state response means the response that is the output of the system due to the inputs only, and we will assume that all initial conditions of the system are zero in this state, and the zero input response means the response due to only the initial conditions, and all the inputs to the system will be zero. Now the state transition matrix satisfies the homogeneous state equation and it represents the free response. Now what is homogeneous and non-homogeneous part of state equation? Now the general form of the state equation is x dot is equal to ax plus bu and y is equal to cx plus du. So this term axt is called the homogeneous part of the state equation, and the term but is known as the non-homogeneous part of the state equation, which is also known as the forcing function. So if we consider the input ut and ut should be is equal to 0, then the equation of the x dot equal to ax plus bu becomes only x dot t is equal to axt, or x dot is equal to ax. It gives the solution of state equation, and it is known as the unforced response of the control system, and it is only governed by the initial condition. Now if the input ut is specified and it is not is equal to 0, then the response obtained is known as the forced response. So now let us consider the state transition matrix, which can be obtained by Laplace transform method of solving the state equation. Now the state equation of the dynamic system is x dot t is equal to ax plus bu, and initial state we can consider that is x0. So for the homogeneous part we can write x dot t is equal to a into xt. Now taking the Laplace transform on both sides, we will get s into xs minus x0 is equal to a into xs, or we can write that xs is equal to si minus a inverse into x0. This x0 denotes the initial state at t is equal to 0. So if we find out xs is equal to si minus a inverse into x0, then in time domain, by using the inverse Laplace method, we can find out that xt, that is equal to Laplace inverse of Si minus A inverse into x0. Now this term Laplace inverse of Si minus A inverse is known as the state transition matrix, and normally the matrix Si minus A inverse is known as the resolvent matrix, and the resolvent matrix is denoted by phi of S. So the phi of S is equal to Si minus A inverse. Now the Laplace inverse of Si minus A inverse gives us the phi of t, and this phi of t is known as the state transition matrix of the given system. Now the state transition matrix is the Laplace transform of the resolvent matrix. Next is the properties of the state transition matrix. Now the state transition matrix satisfies the homogeneous state equation, and it represents the free response of the system. So it governs the response which is excited by the initial conditions only. So we know that phi of t is equal to Laplace inverse of Si minus A inverse, or phi t is equal to e to the power at. Now this e to the power at can be used from the solution x of t is equal to e to the power at into x0, and the solution of the equation gives the zero input response. Now the state transition matrix phi t is dependent only upon the matrix A. Therefore, sometimes it is called the state transition matrix of A. Now, as the name implies, the state transition matrix phi t completely defines the transition of the states from the initial time t is equal to 0 and any time t when the inputs are 0. So the transition from any initial state x0 to any other state xt for any time t greater than equal to 0 is possible, provided that phi of t is known. So state transition matrix has the following properties, that is phi of 0 is equal to identity matrix or I, because we know that phi of t is equal to e to the power at, and e to the power at can be written as identity matrix plus at plus a square t square by 2 factorial, so on. So if you put e to the power at and t is equal to 0 over here, so we will get the phi of 0 becomes identity matrix. And the second property is phi inverse t is equal to phi of minus t. So as we know, phi of t is equal to e to the power at, or we can write phi of t into e to the power minus at is equal to identity matrix. Or if we multiply both sides by phi inverse, then we will get phi inverse t into phi t into e to the power minus at equal to phi inverse t into identity matrix, or e to the power minus at is equal to phi inverse t, or phi inverse t is equal to phi of minus t. So in this way, if we use phi of t is equal to e to the power at, which is the known as the state transition matrix, we can find out the remaining properties also. So phi of minus t into xt, it gives us phi x of 0, and phi of t2 minus t1 into phi of t1 minus t0, it gives us phi of t2 minus t0. Next is phi of t whole to the power k, it gives us phi of k into t. So the property phi of t2 minus t1 into phi of t1 minus t0 equal to phi of t2 minus t0 is known as this transition property of the state transition matrix, and it implies that a state transition process can be divided into number of sequential transitions, because T2 is the final one, T1 is the middle, and T0 is the initial. So it implies that the state transition process will be divided into number of the sequential transitions. So from T0 to T1 and T1 to T2, it generally process can be divided into any number of parts. So we can write that T3 minus T2 into T2 minus T1 into T1 minus T0. It can be written as T3 minus T0 also. Next is the solution of the state equation. So here we will consider the non-homogeneous equation, that means x dot t is equal to ax t plus but, and for the non-homogeneous case we can write that s into xs minus x of 0 is equal to axs plus bus. So from here we can write down x of s is equal to si minus a inverse into x0 plus si minus a inverse into bus after taking the Laplace transform of both sides. Now this I is the identity matrix and this Si minus A inverse matrix is known as the resolvent matrix, and it is represented by phi of S, or phi of S is equal to Si minus A inverse. Now if we take the inverse Laplace transform from this equation, we can write x of t is equal to Laplace inverse of Si minus A inverse into x0 minus Laplace inverse of Si minus A inverse into bus. So x of t, if we want to find out, then x of t is equal to phi of t into x of 0, which is the 0 input response part, and next one is the integration of phi t minus tau into bu tau d tau. So it represents the zero state response of the given system. Now this phi of t actually represents the state transition matrix, and the state transition matrix is the inverse Laplace transform of the resolvent matrix. And this term phi of t into x0, it represents the zero input response, and this phi of t minus tau into bu tau represents the zero state response of the given system, and yt is the total response, which is nothing but the summation of the zero input response and zero state response. Next is the methods which are used to find the state transition matrix. So among these three methods, the method 1 is mostly used, and the method 1 represents that phi of t can be determined by finding the Laplace inverse of the resolvent matrix Si minus A inverse. And the second method is obtaining the state transition matrix by the computation of e to the power at. So the Laplace method is phi of t is equal to e to the power at, or Laplace inverse of Si minus A inverse, and Si minus A inverse can be obtained as adjoint of Si minus A by determinant of Si minus A. And the power series method, that is e to the power at equal to identity matrix plus at plus a square t square by 2 factorial, like this. And third one is the Cayley-Hamiltonian theorem. So let us consider the first method, where we will apply that Si minus A inverse, then we will get the Laplace inverse of this. So here one example has been taken where the system matrix is 0, 1, minus 2 and minus 3. And we have to find out the state transition matrix for this given matrix A. So first we will find out the determinant of Si minus A and Si minus A. So Si minus A becomes S minus 1, 2 and S plus 3, where I is the identity matrix, and if we find out Si minus A, then we will find out the Si minus A inverse, which is actually resolvent matrix. And the resolvent matrix has been found out that S plus 3, 1, minus 2 and S. So the determinant of Si minus A becomes S square plus 3S plus 2, just using the formula. So once we get the Si minus A inverse and determinant of Si minus A. So the phi s becomes s plus 3, 1 minus 2s divided by s square plus 3s plus 2. In the factored form, we can write it s plus 1 into s plus 2. Now we have to find out the Laplace inverse of this phi s. So to find out the Laplace inverse, we have to divide each term of the matrix by the determinant. So it will be s plus 3 by s plus 1 into s plus 2, 1 by s plus 1 into s plus 2, minus 2 by s plus 1 into s plus 2, and then s by s plus 1 into s plus 2. Now to perform the Laplace inverse, we have to break this in the partial fraction method, and as per the partial fraction method, we are finding out that Laplace inverse of s plus 3 divided by s plus 1 into s plus 2 gives us the result 2 into e to the power minus t minus e to the power minus 2t. Similarly, the term 1 by s plus 1 into s plus 2 gives us the result e to the power minus t minus e to the power minus 2t. And remaining term also can be calculated from the same way. So this overall state transition matrix, that is phi of t, which is the Laplace inverse of Si minus A inverse, can be obtained as 2 into e to the power minus t minus e to the power minus 2t, then e to the power minus t minus e to the power minus 2t, next minus 2 e to the power minus t plus 2 into e to the power minus 2t, and the last one is minus of e to the power minus t plus 2 into e to the power minus 2t. So in this way, we can easily find out that Si minus A, then Si minus A inverse, and then Laplace inverse of Si minus A inverse. Next is the second method. In second method, we will use the power series expansion formula. So in the power series expansion formula, we can find out e to the power at is equal to identity matrix plus at plus a square t square plus 2 factorial plus a cube t cube by 3 factorial and so on. So if we put all these values, we can find out this, but in power series method, we actually have to calculate the a square, a cube like this, and it is time consuming. That's why it is not practicable to calculate the higher powers of A. So this method is rarely used to compute the e to the power at. And the Laplace method is very convenient, and generally it is used to compute the e to the power at. But for the small matrices, 2 by 2 matrix or 3 by 3 matrix, we can use this e to the power at or power series formula, and for this minus 2, 0, 1, minus 1, we can find out that it becomes e to the power minus 2t 0, e to the power minus t minus e to the power minus 2t, and e to the power minus t. But it is not practically used for the higher order systems. Next is the third method, which is known as the Cayley-Hamiltonian theorem. Now in power series method, there is one drawback, that it is we need to calculate the A matrix, A square, A cube, and so on. So which is very time consuming, and due to that it is not practicable to calculate the higher powers of A. Now this drawback can be removed by this Cayley-Hamiltonian theorem, because as per Cayley-Hamiltonian theorem, every square matrix satisfies its characteristic equation. That means if we consider any characteristic equation, then we can replace the s square or s cube term by the matrix by own. That means we can write down, replace that s by the system matrix A. So if we consider here a matrix A is given as a 3 by 3 matrix, then as per the Cayley-Hamiltonian theorem, first it will satisfy its own characteristic equation. That's why first we are writing the characteristic equation of the given matrix, and it has been calculated as lambda cube minus lambda square minus 4 lambda plus 4 is equal to 0. Now as per Cayley-Hamiltonian theorem, we can put the system matrix A instead of lambda, then also it will give us the same result. So the final result will be 0. So if we put the system matrix instead of lambda, and then we can calculate this lambda a square minus a cube minus a square minus 4a plus 4, then the final results become 0. So we can prove the Cayley-Hamiltonian theorem in this way. And if we can compute this Cayley-Hamiltonian theorem, we can compute the a square, a cube up to a to the power n without multiplying two matrices. So hope after this video lecture you have got a clear idea about today's topic. Now we will go through some question answer session in context of this video lecture, and you are requested to go through it gradually. Answers are attached at the end of each question.